So this is the setup. So we have a beam which is fixed at one end, the other end is free, and the sensor is placed on the free end. It is wax mounted, adhesive mounted. There are two types of mounting: stud mounting using fastener and adhesive mounting. So I have used wax, and we have mounted the sensor accelerometer on the free end. And it is a piezoelectric accelerometer. It will consist of piezoelectric crystal. So when it subjected to motion, it will produce electromotive force that is directly proportional to the acceleration. So the sensitivity of the sensor is given in the calibration. So in this manufacturer, they have provided a calibration data sheet. It says 9.97 millivolts per G. So this sensor is connected to the data acquisition system through the BNC cable. So here we have data acquisition system, National Instruments NI 9230. So there are 3 channels. So we can see it is connected to the channel AI0. So it is connected to the channel AI0, and there is another channel 1 and 2. And finally this data acquisition system is connected to the computer or system, right? So now we will run the program. So you can run the program, and that will configure all the settings. So it will start acquiring. So we will give an initial disturbance. So we will give a small disturbance. And so the free vibration test is nothing but giving a small initial disturbance to the structure and then remove the disturbance, so that will vibrate in its own natural frequency. That is called free vibration. So we begin with launching the MATLAB software. Right. So the first section deals with the data acquisition system configuration and setup of DAC. So the first line, CLC clear close all. So this will reset the MATLAB environment completely. So CLC will clear the command window text, clear, wipes all the workspace variables from the memory, and closes all the open figure windows. So this line of command D is equal to DAC NI. So this create DAC session object for National Instruments hardware. The variable D is your handle to the physical device of all subsequent commands. Right. So next we do the user settings. So f of s equal to 10,240, meaning the DAC records 10,240 data points every second. Higher the sampling rate, our resolution will be more fine resolution. Then we set duration equal to 5, which means the recording length is 5 seconds. So the total sample collected will be your f of s into duration, which will be around 51,200. So then it is the input value sensitivity. So sensitivity is 9.97 millivolt per G, which means this value comes from the accelerometer calibration sheet. So based on that, we will give the input value to the MATLAB software. So the MATLAB uses this to convert the raw voltage into acceleration unit in terms of G. So the next one is device ID and channel ID, which is nothing but identifying the physical hardware slot and analog input pin which is used, right? So it says that we are using the chassis slot 1 module 1, and AA0 is nothing but analog input channel 0. Right? So next we come for so this statement, this code is nothing but applying the sample rate to the DAG session object. So without this, the hardware does not know how fast to sample, right? So next one is registering. So register the channel as an IEPE accelerometer type. So this is an accelerometer type. This activates the bias current supply. The sensor need to operate. And next one is sensitivity. So this will tell the MATLAB sensor configuration. From this point, all the acquired data is to be returned in the unit of G, not the voltage. Then finally, all the formatted test configuration are logged into the command window using the print function. So always log your settings so that the experiment is reproducible later. So to summarize this, we begin by clearing the MATLAB environment, command window, variables, and figure. So we can start from a clean state. We then create a DAG session object tied to our National Instrument hardware. So think of this object as a control panel for the physical device. So we define our three key measurement parameters: sampling rate at 10,240 hertz, a duration of 5 seconds, and the sensitivity of 9.97 millivolts per G, a value that will be read directly from our accelerometer datasheet. We then register our analog input channel as IEPE accelerometer type, which will automatically activate the current excitation the sensor needs, and we assign the sensitivity to the MATLAB, which will handle the data already converted into the unit of G. So next is acquire data. So here first, uh, so this one pre-computes the expected sample count, that is 10,240 into 5, 51,200. So this is used to build the time vector. So here this one will build the a column vector of timestamp in seconds. So the timestamp will start from 0 second and will end at 4.999 seconds, right? So next we will start acquiring the uh, data, and this one will block read. So this program pauses here until all 5 seconds of data are collected, then returns a numeric matrix in the unit of gravity, right? So then the data acquisition is complete. Then finally we will report the largest instantaneous acceleration recorded, and finally we will quickly check if this is unexpectedly large or zero, something is wrong with the setup. So that this will do the quick check. So to summarize, the data acquisition section is deliberately simple. We compute how many samples we expect, 51,200, then build a matching time axis. The read command is blocking a call. The program stops here and wait patiently while the hardware fills the buffer, which is with the exactly 5 seconds of vibration data. So when it returns the variable buff already contains the acceleration values in G, the MATLAB handle the unit conversion internally. So we immediately print the peak amplitude as a quick sanity check before moving to the analysis. So now the next section is time domain plot. So here, so this one opens a new named figure window. So the number title is off, removes default figure 1 prefix from the title bar. Then we are plotting the acceleration versus time as a thin blue solid line. This indicates it is a blue color, and the line width is 0.8. And next one, so this one locks the x-axis to exactly the recording window of 0.0 to 5 seconds. So this prevents MATLAB from adding the automated padding. Then finally the y limit. So this one will auto scale the y-axis up to like 120 percentage of the peak amplitude plus a tiny fixed offset, so the signal never touches the plot border. So the time domain plot will give us the most direct view of the vibration signal, the raw acceleration over time. So we use this blue thin line to preserve the waveform detail, and we notice that y-axis limits are computed dynamically from the actual peak value and scaled to 120% with a small safety offset. This means that the plot always looks correct regardless of whether the vibration is tiny or large. So now the next section is FFT, the frequency domain analysis. So here we store the total sample count. This n determines the FFT size and therefore the frequency resolution. So the frequency resolution would be f of s divided by n. So which is 10,240 divided by 51,200, that is equal to 0.2 hertz per bin, right? So then we perform Hanning window to reduce the spectral leakage. So here, so Han n generates a bell-shaped taper of n, on which points 0 to 1 and then 0. So then finally, this performs element-wise multiplication and tapers the signal to 0 at both the ends. So this prevents frequencies smearing caused by very sharp signal edges. Right? So then we compute the fast Fourier transform and normalize the magnitude. So this FFT function converts the time domain to the frequency domain, and it extracts the absolute magnitude uh, and ignores the phase and divide by the n scales of amplitudes to match the physical units. So the next line is here. This extracts a single-sided spectrum, which is positive frequency, and compensates for disregarding the other half, mirror half. So FFT output is generally symmetric for real signal. The upper half is redundant. So doubling the restores the correct amplitude, right? So that is performed here. Then this builds the frequency axis in hertz. So each bin k corresponds to the frequency k multiplied by f of s into n. So it runs from 0 hertz to the f of s divided by 2 up to the 5120 hertz. Right? Then we will plot the f of t. So this one will plot the amplitude spectrum as a red line zoomed from 0 to 100 hertz. You can see here it is zoomed from 0 to 100 hertz to focus on the range, the operating range, or the structural or resonance range. Right? Then we identify the dominant frequency or peak frequency, skipping the DC bin at the index of 1. Then we annotate the peak on the plot with a black circle marker, right? So this one will annotate the natural frequency with a black circle marker and the text label showing the frequency as well as the amplitude. So this one forms the analytical core, the fast Fourier transform. The FFT decomposes our time domain signal into its frequency components. So this is will answer the question which frequency carries the most vibrant energy. So before computing the FFT, we apply the Hanning window. So this is essential. So without it, the abrupt start and end of 5-second recording will create sharp edges that may smear the energy across many frequency bands. So this problem is called spectral leakage. So the Hanning window generally tapers the signal from zero at the board end and keeping the frequency peak very sharp and located. So after the FFT, we extract only the first half of the output, the positive frequencies, because the second half is mathematical mirror image of the real valued signal. So we double all the interior amplitudes to compensate. So the frequency axis is built. So each bin corresponds to specific frequency in hertz. And finally, we automatically detect the dominant vibration frequency. So this is our primary diagnostic result of vibration analysis. That is determination of natural frequency. So now we have come to the last section, saving the result, right? So here we are saving all the key variables to a .mat file in the current working directory. So here buff represents the raw acceleration data, the time axis, then your frequency axis, then amplitude spectrum, the meta. These are your metadata sensitivity and duration for reproducibility. So the last step, it saves everything into a .mat file, and we save not just the raw data but also the computed frequency axis, the spectrum, all the acquisition parameters. Saving the metadata alongside the measurement is a discipline worth building from the day one. 6 months from now, if when you revisit this file, you will know exactly what hardware settings and sensor calibration produced these results without needing to find the original script. So now first click will run this program and give a small disturbance to this beam, and this will capture the vibration. So now you can see the FFT spectrum and also the time domain plot. So this shows an underdamped system. So from this time domain plot, we can find the consecutive ratio of consecutive amplitudes to find logarithmic decrement, and then we can find the damping ratio. And similarly, from this frequency domain plot, we can find the natural frequency, the first peak. So this shows the natural frequency. The value is 6.4. So the frequency is 6.4 hertz, and we can also see the impulse, that is 0.075 gravity. Okay. So from this also, using half power method, we can find the damping ratio. So this is the FFT analysis, time domain plot and frequency domain plot. So now if you run the program and if you give initial disturbance to the beam, and it will capture the signal for 5 seconds. Right? So after capturing the signal, we can find the data acquired. So this is our time domain plot. We can see that the amplitude is decaying over a period of time. So this is an underdamped system, right? And also we can find the amplitudes here. So the first peak is around 0.87 G, and after 1, 2, 3, 4, 5 cycles, the amplitude reduces to 0.45 G. So this ratio of consecutive amplitudes are used to determine the logarithmic decrement. From that, we can find damping ratio using logarithmic decrement method. So this is the observation from time domain plot. Then there is the FFT spectrum, frequency domain plot, where we can see the natural frequency. The first peak corresponds to first natural frequency. It is 6.4 hertz, and the impulse, the A max, the amplitude, maximum amplitude is 0.075 G. And if I divide by root 2, and that is used to draw the horizontal line in here, and the horizontal line cuts this peak both left side and right side, and the corresponding frequency on left side and the corresponding frequency on right sides give the off power bandwidth. So from that we can find the damping ratio also using off power method, right? So this is called uh, FFT analysis, where we have found the natural frequency and damping ratio.